Good morning, everybody. We are now moving forward. We finished up our first exam. Those grades will be posted. If they haven't already been posted by the time you watch this video, they will be posted very soon. So we're going to start our second unit, and hopefully we'll start noticing a little more of a flow and smooth transitions between all of our sections now that we're kind of returning a little bit to more of a normal routine with school. What we're looking at today is properties of linear functions and linear models. This really should be a fairly straightforward review of things that we have discussed in this class and things you've discussed in other prior math classes, such as your Algebra 2 and your Algebra 1 class. We're going to first define a linear function. A linear function is always of the form y equals mx plus b, or f of x equals mx plus b, where m is the slope of the line and b is the y-intercept of that line. And the domain of any linear function is always going to be all real numbers. And the same is true for the range as well, unless it is a constant function. For example, y equals 3. The range of y equals 3 is always going to be 3, but its domain is still all real numbers. So for example 1 just says graph the linear function negative 3x plus 7. What are the domain and range of f? Well, that's going to be pretty straightforward to graph. We have a slope. If we just write this out, y equals mx plus b. And if I write the given equation directly below that, we can see that the slope is negative 3 and that the y-intercept is positive 7. So if I transfer this over to my graph, I have a y-intercept of positive 7. So let me go up to 7 on the y-axis. 1, 2, 3, 4, 5, 6, 7. And my slope is negative 3, which means I go down 3 and to the right 1. And I can do that a couple of times if I want to. But there is the points that I can draw my line through to create this this graph. So I'm going to try to do this as best I can, which wasn't the best in the world, but that's going to be the graph of the line. Y equals negative 3x plus 7. The domain is all real numbers, and the range also will be all real numbers. If you just heard a loud bang, they're working on something down the hallway, and that's going to happen. I don't know what's going on. Sorry about that. Had to take a phone call. Let's see, where was I? Okay, so we have the domain and the range. In both cases, it's all real numbers. So what that just simply means is that we can put in any x value we want, and we're going to generate a new y value. So in both cases, all real numbers would be the possibilities that we would come up with. Now, linear functions have a constant average rate of change. The average rate of change for any linear function is always just going to be equal to its slope. It's the change in y over the change in x, and that's what this notation right here simply means. Delta y over delta x is change in y over change in x, which corresponds to our slope. That's the average rate of change of any given function. If you're interested in studying this proof, I would highly encourage you to go ahead and do that. If you're not interested in this proof, skip it and go on. It just depends on how much you want to understand a little bit deeper with the mathematics, but this proof is fairly straightforward, and you can look at it if you'd like. So we're going to jump to our first example, our second example rather, and we're talking about a strain of E. coli known as BU 397 RECA 441, which is a really fantastic name for a strain of E. coli. It's placed in a petri dish at 30 degrees Celsius and allowed to grow. The data that's shown in the table, they are collected. The population is measured in grams and the time is in hours. Plot the ordered pairs in the Cartesian plane. Then use the average rate of change to determine whether or not the function is linear. So the first thing we want to do is plot these points. I'm going to let the x-axis, that's going to be my time. So let me change my pen color. We have 0, 1 hour, 2, 3, 4, 5, and 6 hours. And our population in grams, try to figure out what my scale might be. Maybe we'll go up by tenths here, so 0.2, 0.3, 0.4. And I'm going to start plotting these points. So at 0 hours, so that's the initial time. That's when the bacteria is placed in the Petri dish. We're at 0.09. Then after 1 hour, it's at 0.12. At 2 hours, it's 0.16. 3 hours, 0.22. 4, 0.29. And then 5 is 0.39. Now, the way the scale is on my particular drawing here, this may appear to be somewhat linear. If I kind of connect these points, you can see that this does start to curve up just a little bit, and we start to notice that's a curve, and this actually is exponential growth. But we want to verify, does this indicate, just the table alone, does it indicate to us whether or not we have a linear function? And so we have to compare the values from one x value to the next to determine whether or not this is linear. And if it is linear, then we're going to notice some consistency in the average rate of change between points. And so I'm going to show you by example here what we're talking about. So with our first point, we have the time is 0 hours and our corresponding y value is 0.09. And then our next time is 1 hour, and our corresponding y value is 0.12. So we're going to focus first on these 2 points. So let's find the average rate of change, which we said would be the slope. And again, it's the same calculation as we're always used to doing. It's y2 minus y1 over x2 minus x1. So for those first 2 numbers, we're just going to use 0.12 minus 0.09 over 1 minus 0. And when we calculate this slope, we get 0.03. That's for our first 2 ordered pairs. Then I want to compare our next 2 ordered pairs. And I'm going to do this in purple. So now I'm going from 1 hour to 2 hours, and I'm going to compare this slope. And again, it's going to be y2 minus y1 over x2 minus x1. And so these values are going to be 0.16 minus 0.12 over 2 minus 1. And that is going to simplify to 0.04. Okay, so the difference between those two, and as far as the average rate of change, is very negligible. We could at this point say, yes, this appears to be linear. But we need to keep going to ensure what we're looking at here. So now we're going to do the next 2 ordered pairs, where we're going from 2 to 3. And I hope this green shows up fairly well for you, that you can see it on your screen. And when I simplify that, I get 0.06. So now I'm starting to maybe detect that there is not a linear pattern here, because these numbers continue to go up. But let's just take it one step further. And we have 0.29, 0.22. And I'm going to do just one more from 4 to 5. And this will take care of all of our values. All right, so we are only looking at these average rates of change between successive x values and their corresponding y values. And we notice that there is no consistency in these average rates of change for each one of these corresponding values. So what we can make, the claim that we can make now, is that this is not linear. Later on, we'll discover that this is in fact exponential. But we can clearly see, though, it's not linear. For it to be linear, there would have to be some consistency in the values that we see in this column right here. But we notice in this particular case, they are all constantly increasing, which means this is not a linear rate of change. Now, if we look at the second part of this example, we're looking at something very similar. Now we're talking about the average number of heartbeats of a healthy individual during a 15-second interval of time while they're exercising. We're going to plot the ordered pairs in the Cartesian plane, use the average rate of change to determine whether or not this is linear. So again, we will put on the x-axis our age, and I'll go up by 10. So 10, 20, 30. I'm going to end up neglecting the 70-year-old there. And then my corresponding y values. I'm going to go up by 10 here as well. 10. And let's plot our points. So at 20, it's 50. At 30, it's 47.5. 40 is 45. 50 is 42.5. 60 is 40. And this, if I plot a line through here, that one does appear certainly to be linear. But again, we're going to check it, doing the same thing that we did before. We're going to compare our first two values, these XY ordered pairs. So our first slope is going to be 47.5 minus 50 over 30 minus 20. And that comes out to be negative 0.25. Then I'm going to compare the next two sets of ordered pairs. And again, I get negative 0.25. Compare the next two sets of ordered pairs. And then we're going to compare another set of ordered pairs. And I'm not going to keep on going with this one because we can see right now, looking at this right-hand column, our values are constant. The average rate of change from one x value to the next with respect to their corresponding y values, it is very consistent, and they are all equal. So this would be a linear change between, as it relates heartbeat and age. So to determine whether a linear function is increasing, decreasing, or constant, all you have to do is look at the slope. If the slope is positive, then the function is increasing. If the slope is negative, then the function is decreasing. If there is no slope, then that function is constant. And we will see that here in example 3. Determine whether the following linear functions are increasing, decreasing, or constant. For part A, my value for m is 5. And really, it doesn't even matter what the number is. It just matters what the sign is. It is a positive 5. So that means this is increasing. For part B, m is negative 2. Again, we're only interested in the sign. Because it is negative, we have a decreasing function. For part C, m is positive 3/4. Because it is positive, that means we have an increasing function. And then finally, for part D, m, there is no m value. M is 0. So because we have no slope, we have a constant function. All right. Finding the zero of a linear function. So any real number that's a zero of a function is just where that function would cross, would give a y value of 0. So where does it cross the x-axis? And so when we're looking for the 0 of a function, trying to find where it crosses the x-axis, we simply set the function itself equal to 0, solve for x. So for part A, does the function have a 0? It is decreasing because we have this negative 1/2, so it's going to have to cross the x-axis at some point. So for part A, yes, it has a 0. For part B, we're going to find the 0. So we set the function equal to 0 and solve for x. So we subtract 2 from both sides. Then we divide both sides by 1/2 and we get negative 4 is equal to x. So this function has a 0 at, that's negative 2, so that should be positive 4. So it does have a 0 at positive 4. For part C, it just says, what happened? Oh, my computer is not cooperating. There we go. For part C, it just simply says to use the 0 along with the y-intercept to graph f. So this is going to be a very crude graph. But we see that the y-intercept is positive 2. And we have the 0 is at positive 4. So our graph will look something like this. So that line clearly has a negative slope, and we know then that we have approximately come up with the correct graph for this particular problem. And then finally for part D, it says solve f of x is greater than 0. So all we have to do now is take our function and make it greater than or equal to 0, or sorry, in this case just greater than 0. And we're going to solve for x, so we subtract the 2, divide both sides by negative 1/2. When we divide by a negative, we have to flip the inequality, and so what we end up with is that 4 is greater than x, or writing it out this way, x is less than 4. So for every value where x is less than 4, this function will be greater than 0. And we can see that in our graph right here. Every value to the left of 4 is going to be less than 4, and the graph itself, you see, lies above the x-axis, making it positive or greater than 0. Building a linear model from a verbal description. When the average rate of change of a function is constant, a linear function can model the relation between the two variables. So when we think back to the age and the heartbeat, we could actually have come up with an equation that would model that because the rate of change was constant. So for example, here we have that a recycling company pays 52 cents per pound for aluminum. Then the relation between the price paid and the pounds recycled can be modeled as 0.52x, so 52 cents per pound. And that's just a very simplistic model. We'll jump in with example 5 and get a little bit more in depth with this explanation. Sorry, I had to answer another call. Okay, so here we're going to look at example 5, and we have book value is the value of an asset that a company uses to create its balance sheet. Some companies depreciate assets using a straight line depreciation, so that the value of the asset declines by a fixed amount each year. The amount of the decline depends on the useful life that the company assigns to the asset. So for our example, we're going to suppose that a company just purchased a fleet of new cars for its sales force at a cost of $31,500 per car. The company chooses to depreciate each vehicle using a straight line method over 7 years. This means that each car will depreciate by an amount of $31,500 divided by 7, which is $4,500 per year. If you'll notice, this is our slope. It's the original value divided by 7 years, and that gives us the slope of this particular equation. For part A, we just want to write a linear function that expresses the book value V of each car as a function of its age. That part is relatively simple. For part A, the value of the car as a function of its age. The car starts out at $31,500. And since it's depreciating, that means it's going down in value. So that's $31,500 minus $4,500 per year. If we wrote it in slope-intercept form, it would be negative 4,500x plus 31,500. That's part A. Part B, graph the linear function. I hope I gave myself enough room to do this, but let's put in the number of years on the x-axis. And then along the y-axis, let's go up by $4,500 and see if this works. It did work. Okay. So our y-intercept in this case is 31,500, and our slope is negative 4,500 per year. So each year it's decreasing by $4,500, and that's going to give me this line for my function. What is the book value of each car after 3 years? So after 3 years, we can simply use our graph if we wanted to. If we go up from 3, we see that it is $18,000. And this is part C. And we can verify that using our expression that we created. So again, we can do V of 3 is equal to 31,500 minus 4,500 times 3, and that gives us 31,500 minus 13,500, which does in fact equal $18,000. Interpret the slope. So the slope is just the average rate of change of the vehicle, which means that the cars decrease in value by an average rate of $4,500. And part E, when will the book value of each car be $9,000? We can again look at the graph and we can see that 9,000 corresponds to 5 years. But in a similar fashion to what we did in part C, we can do the same thing for part E. We just take this function and we set it equal to 9,000, and we solve for x in this case. So if we subtract 31,500 from both sides, we're going to end up with negative $22,500. Divide both sides by negative 4,500, and we get x is equal to 5. So we get 5 years. I'm going to pause for a minute, plug my computer up, and I'll be right back. Example 6 is going to be kind of similar to what we just did in example 5, except this one we're given two different functions, and we're going to work with these two functions independently and then simultaneously. The quantity of a supplied good is the amount of a product that the company is willing to make available for sale at a given price. And then the quantity that's demanded is the amount of product that consumers are willing to purchase at a given price. So right here in our example, we have two functions. We have a supply function and a demand function. The supply function is on the company side of it. The demand function is what the consumer is wanting to, how many objects they're willing to purchase at some price given by the variable P. P is the price in dollars of a cell phone. So that's what we're looking at here. The equilibrium price of a product is defined as the price at which quantity supplied equals the quantity demanded. That is, the equilibrium price is the price at which supply equals demand. Find the equilibrium price of cell phones. What's the equilibrium quantity or demanded or supplied at the equilibrium price? All we have to do for part A is set these two functions equal to one another. This is where S of P equals D of P. So S of P is 30P minus 900 equals the demand function and we can start moving our variables from one side to the other, and moving our constants from one side to the other. So let's add 7.5p to both sides. And then we'll add 900 to both sides. And then finally we divide both sides by 37.5. And what we get is an equilibrium price of $100. That's the, let me highlight it here for you. Right here, find the equilibrium price of cell phones. The second part of this says what's the equilibrium quantity. So because we've set both of these functions equal to each other, it doesn't matter which one we substitute that $100 into. Both functions should come out with the exact same value. So I'm going to use the supply function, and I'm going to put in 100 for the price. And that's going to give me 30 times 100 minus 900. So 30 times 100 is 3,000. When I subtract that, I get 2,100. So the supply of 2,100 phones would be equal to the demand of 2,100 phones, and that would be at a price of $100. Determine the prices for which the quantity supplied is greater than the quantity demanded. This one doesn't take a whole lot of thought to go through here, but we have B. This is part B. We're looking at where S of P is greater than the demand. So when does the supply exceed the demand? And that's when the company would start losing money. If you look at part A, we did S of P equals D of P. It's not going to be any different. The only thing is we've changed our symbol here in the middle from an equal sign to a greater than. So without going through all the calculations again, we would just end up with P greater than 100. So when the price is over $100, then the company is going to have a greater supply than the consumer demand, and they will probably end up with a surplus sitting in their warehouse. Now let's graph these two functions on the same coordinate plane, and you'll see that equilibrium point is where they intersect one another. For this function, let me see what I want to do. 20, 40, 60. Yeah, I think this will work. Okay, so my variable X, this also corresponds to P, so that's the price. And then my demand will be given by, let's go 200. All right, so there's my scale for this particular graph. I'm going to do the supply in blue, so S of P will be the blue line, and that function is given by 30p minus 900. So we have a y-intercept of negative 900, which will put that down here, and we would have an x-intercept of 30. So this graph is going to, let's see, 100. I didn't make my scale big enough on the left. That graph is going to look like this, and then my demand function, I will do it in pink. We have a y-intercept of 2850, which is going to be way up here above my scale. That's what I was talking about a minute ago, but our slope is negative 7.5. That graph will look something like this, and they'll intersect, well, that's pretty close to 100 and 2100. That's what we found in parts A, or actually in part A, was at $100. The supply and demand was equal to 2100. But we can, so what this shows is basically we can do it algebraically like we did in part A, and then in part C we can also verify it graphically, finding the two intersections of the equations, and that will be our equilibrium point. So here's your suggested problems. I'll be getting the second video out here shortly. If you have questions, remember to ask me. Hope you guys are doing well.